Hi student, good morning. Let's start for the preparation of the quantitative analyst and enter into the world where the life is waiting for you, the opportunities. So today's we will start the learning the core mathematics and statistics first part, that is the linear algebra. So in linear algebra, we will look at in details the vectors, matrices, eigenvalues, and eigenvectors, and some applications in portfolio optimization theory. So let me give you the details on that each topic, what we are considering today, and what are the key terms we will use today for that understanding. So let's first start with the vectors. So what is the definitions of vector? A vector is a one dimensional array of number representing the quantities in finance. So there is a slightly difference between the vectors and matrices. So you can see on my screen, this is a vector, that is a one dimensional array, and you can see the matrices, there is a two or more dimensional array. We can write the matrices in a such a way, there are the relationship between each term covariance or correlation between each term. So that the matrice the vectors as a, single single array, okay, one dimensional array. So vector additions, we simply, if we want to two vectors and add them, so we can add them with, you can see here, so add each first term and then add each second term. It is just the addition of the each terms, and then the scalar multiplication for the vector product, that c is the constant product and v is a vector, you know, this is a v vector. So simply the product of the c into v first term and c into v into second term, and the dot product of the vector are the summation of I. If we consider the dot product, measure the alignment and correlation between two vectors in a such a way that u dot v is equal to summation of I is equal to 1 to n ui plus vi. So add these terms in a dot product, and the application is portfolio return, rpv measure these thing, and much more problems we can solve that with the help of the dot products in the quantitative finance. So let's move the next and most important topics, that is a matrices. So first look at the definition of matrices, and then we will move the next topic. So matrices is a two-dimensional array representing the relationships and transformation or data structure in finance. For the common example of the matrices, covariance matrix measure how assets move together. If there are the uh, two different assets and they have some relation, they are positively correlated or negatively correlated, or there is no correlation, that we measure in the form of matrices. And the return matrix, so row represent time period, column represent assets return. So let's first look at the key properties of the matrices. First is the transpose of matrix. So in transpose of matrix, we just simply convert the row element into the column element and the column element into the row element. So let me write, for if suppose we have the matrix A, let's write the elements A1, 4, A7, 4, 8, 9, or the, let's consider 3 by 3 matrix. Okay, this is a 3 by 3 matrix. So why we call it 3 by 3 matrix? There is a 3 rows and the 3 columns in that matrix, so we call it as a 3 by 3 matrix. Let's write down the transpose of A T, we write as a transpose of A. Let's simply write a transpose of A. It's a simple, is equal to transpose and select your matrix and just put on the enter button. So we will get the transpose of A matrix. That is the simple way to get the transpose of matrix A. So let's move to the another point for here. Okay, let's the inverse matrix. There is the another concept, singular and non-singular matrix. We will look another terms, the inverse matrix, the matrix which is a non-singular, so we call it as a determinant of that matrix is not equal to 0, that matrix we call as a non-singular matrix, and such matrix is only inverse exist. Otherwise there is no inverse exist. So the inverse of matrix, if we consider the matrix A inverse, so let me write A and there a square there I. So that A inverse matrix. So we simply write the inverse of matrix is equal. Let consider the entire cell. Okay, let me write for you. Let consider the entire 3 by 3 matrix. Oh no, sorry. Then put enter to M. So there is we use the M inverse functionality for that matrix and select this matrix and just enter the button. So this is the inverse matrix of A, matrix inverse. We will get simply use the functionality of M inverse to calculate the inverse of the matrix. And then further we will move to the next topic, identity matrix. So simple, the a square matrix whose one on diagonal and other zeros elsewhere. So let me write the 3 by 3 matrix as the inverse matrix. So if we consider that is the I is the inverse matrix, so 1 0 0 0 1 uh, 0 0 0 and 1. This is a simple inverse matrix. So this matrix we call as a inverse matrix. So let's look on the matrix operations. It's most important on the matrix operation. So first operation, let me look at the addition of the two matrix. So suppose there is a two matrix A, we have the matrix A already. Let's consider the matrix B. So it has the element 2 4 5 2 4 4 3. Simply if we want to add two matrix, then just write that A plus B is equal to, let's select 3 by 3 first, and then put enter M sum, and then enter this thing, enter this thing, and then just enter. So we will get the addition of that matrix. Okay, let me go for you on that screen. So let's look at the properties of the matrices. So go to the some properties. Cumulative properties satisfy A plus B is equal to B plus A. If two matrices, one matrix is A and another matrix is B, then A plus B is equal to B plus A. And the associative property, if we consider the three matrix and bracket of A plus B plus C is equal to the A plus bracket of B plus C. These properties satisfy the matrix if we consider every matrix. And then the scalar multiplication of each matrix. If we consider as a C is a constant and A is a matrix, so that C is the add at product of each level. So that is functionality is also satisfy. And then we will move to the matrix multiplication, cumulative. A B not satisfy in general, the matrices A into B is not equal to B into A. So associate property is satisfy in the matrices A into BC is equal to A into BC. So descriptive property is also satisfy, distributive property is also satisfy in the matrices. So that is, let's move to the matrix multiplication. So let's we multiply these A plus B matrix. So A into B matrix. So it's, you just simply put equal M. Let me consider the 3 by 3 cells first, because it's not the, oh no, shit. Let me consider. Let's enter M M mult and then select the A matrix. Simply select the B matrix and just enter button. So we will get the product of A plus B. Simple functionality is MM mult. We use the matrix multiplication. Okay, and then the following properties are satisfy the transpose properties. If we consider the two matrices, the transpose of the A. We know that the in a transpose matrix, row become a column and column become a row, and then other next time row become a column and column become a row, then we will get the same matrix as we have before. If A plus B is equal is transposed to the AT plus BT, it's also satisfy the product of AT BT, product of A into B raised to T is also B raised to T and A raised to T, that is satisfy determinant of matrix. How to calculate the determinant of matrix? It's the most important concept. If we want to calculate the determinant of matrix A, let's consider the determinant of matrix A, M determinant, and then we have just select the matrix, press and enter button, but we made some mistakes, so we need to select the three cells. Okay, 122 is a determinant of matrix A. So let's simply use M determinant and select the matrix. Let's we consider the determinant of matrix B. So M determinant, and then select the matrix B and just put enter button. So a determinant of A is 10. Just simple with the views of the help. So we just write determinant in that way. The determinant is scalar value associated with vector matrix and denoted by determinant of A or bracket of properties of the determinant of A. Determinant of A transpose is equal to the determinant of A. Determinant of AB is equal to determinant of A into determinant of B. Determinant. If A is invertible, that then determinant of A inverse is equal to 1 upon A. Okay, if matrix is invertible, so this is a satisfy. And if determinant is equal to, then A is singular or non-invertible. If determinant of A is equal to 0, then a singular matrix, and that is non-invertible matrix. So let's move to the inverse of matrix. Inverse of matrix, that is the functionality is also most important for the quantitative analysis perspective. The inverse of square matrix A denoted by A inverse, and the product of two inverse matrix is always identity matrix. Let's keep in mind. And the inverse of matrix inverse is always the same matrix. If you have a two matrix A B, and if you consider the product of these two matrix and they put their inverse, then you will get the answers as B inverse into A inverse. So these are also the property of the matrix. And if we can consider the matrix transpose of matrix A, it is a bracket of inverse, then we will get the inverse of A and their transpose so that is the another inverse of matrix functionality. So let's move to the identity matrix. So product of the identity matrix is always the same matrix A, so that is the identity transpose is equal to identity matrix. Rank of matrix. A rank of matrix A is maximum number of linearly dependent row and column. Linearly dependent row and column. Okay, symmetrics and skew matrices, they are orthogonal. Let's move to the some examples on the matrices. So eigenvalues, square values. So let's first consider the rank symmetry and the skew symmetric matrix. So symmetry matrix we consider as a is equal to A transpose. That matrix we called as a symmetric matrix. Symmetric matrix we called as a, if the matrix A is equal to A transpose, so this matrix is called as the symmetric matrix. And skew symmetric matrix is A transpose is minus of A, so this matrix we call as a symmetric matrix. Let's consider the, let me explain you the symmetric matrix. If matrix 1 2 2 and then 2 2, and this matrix is 3 2 4 and 4. If this matrix, if we consider the determinant transpose, we will get the same matrix. So it's, if we consider the equal sign for this matrix and put on the transpose, then we will get the matrix A itself. Let's consider same matrix as we have. So this matrix we called as a symmetric matrix. And then the A transpose is minus A matrix is also the skew symmetric matrix. And then we will move to the orthogonal matrix. A square matrix Q is orthogonal if Q transpose and Q is identity matrix. If matrix Q we call as a orthogonal matrix if it satisfy the Q transpose and the Q product of the Q transpose and Q is the identical matrix. So we called as the properties as Q inverse and Q is same column and row of Q orthogonal. So let's most important topic, that is the eigenvalue and eigenvector. For a square matrix A, if Ax is equal to lambda x, then lambda is the eigenvalue and x is the eigenvector. Let's keep in mind. For a square matrix A, if Ax is equal to lambda x, then lambda is the eigenvalue and x is a eigenvector. So properties eigenvalues of A and A transpose are same. Some eigenvalues trans of A is a diagonal element. Okay. Positive definite matrix. A matrix A is positive definite if AT for all non-zero vectors, all A and positive. So that is a way the matrix is we